For number 5, we're looking to see if there is a relationship between a person's age and their HDL cholesterol. So the table of data here, I'm going to open it in StatCrunch. And to get to that screen I was just at, you'd want to go to Stat. And we're looking at correlations here, which gives us a regression line. So regression and simple linear. We're just looking to see if there's a linear relationship. So our explanatory variable is going to be a person's age. We're going to see if that can be a way to predict our response variable, which is their cholesterol levels. And that's about all we need to input for this particular problem. And we hit compute. And it gives us this information here. The correlation coefficient pops up right away. So I'll jump to that part of the problem. 0.047. Rounded to negative 0.048. And does a linear relation exist between age and cholesterol levels? Well, here's a table of critical values. And so based off of our sample size, there's 5 pairs of data in our sample. We would want a correlation coefficient to be at least this value or higher. And since 0.04 is quite a bit below that, it doesn't meet the threshold, so there's little or no evidence of a linear association between these variables. And now for the part I skipped over, the scatter plot. You saw that in StatCrunch. It looked slightly different than this just because the scale is a little different. But notice here we have this little triangle of data, then there's one really low point and one point up there with the triangle. Here, notice the x-axis starts at 25. Let me jump back into StatCrunch. If we click this arrow here, it should take us to the scatter plot. And notice our x-axis starts at 38. So it's more compacted around where our data points are. So our plot looks a little different, but we still have that triangle of data. And then the next point's really low down, and then the final point's up, kind of at the triangle level. So that is the correct scatter plot. For number 6, we're going to find the least squares regression line and then graph it on the scatter diagram. So I'm going to open this data here in StatCrunch, and I would want to go to Stat, Regression, and we're looking for a linear regression. Now our x variable is just called x, our y variable is just called y, and then we want to hit compute. And what we get back here, it shows us the equation of a least squares regression line. Now notice it has the intercept point first, and then the slope multiplied by x is second. So when you're typing it in, make sure you don't get those numbers backwards. They have the value multiplied by x listed first. So this is the equation of the best fit line, the least squares regression line that passes as close to all the points in our data set as possible. And we can use that line then to make predictions about different values for x. We plug them in and we see what the corresponding y value would be for our prediction. Again, you can see the scatter plot with the line drawn right here. Notice our scale starts at 3 and these start at 0, so they look slightly different, but just focus on where the points are above and below the line. We have above, pretty much on, and then below, above, above. So looking at that, above, pretty much on, below, above, above. B is the correct choice here for our scatter plot. For number 7, again, going to rely on StatCrunch. And we're going to find our least squares regression line. So open the data in StatCrunch, Stat, Regression, Simple Linear. Our x variable, our explanatory is called x, our response is just called y here. We want to hit compute. And so we get our equation, our least squares regression line. And then we just need to look down this bottom table here, and it has the information we need for the sum of the squared residuals. And so pulling that back up, SS stands for sum of the squares, and error is our residuals. So this right here, the intersection of that row and that column, that is the sum of the squared residuals that you would want to input for your answer. And so let's take a look at the scatter plot, talking about the residuals. It's how far away the actual data points are, their y value is, from the predicted y value that we get from the least squared regression line. So just measuring that distance, how far away each point is from the line, just going straight up and down, that is the residual. And if we wanted to know what the total kind of distance is, all our points are away, we couldn't just add the residuals of all the points together, because the points above like this would have a positive residual, they're above the line, and then points below like this would end up having a negative residual because they're below the line. And so those positive and negatives would cancel out. But if we square all those differences first, all those residuals, when you square a number, the answer is always positive. So when we square our residuals, we'd have a bunch of positive numbers that we're adding up. And that's what we're doing here, calculating the sum of the squared residuals. And it's listed right here in the column. In number 8, we're trying to see the relationship between the weight of a gas-powered car, that's our explanatory variable, and what effect the weight has then on our response variable, which is the gas mileage of that car. And so we have a table of data here. We want to open it in StatCrunch. And over in StatCrunch, we're going to go Stat, Regression, Simple Linear. And our explanatory variable is the weight. Our response is the miles per gallon that car gets. And we want to hit Compute. So right away we get our regression equation right here. And so after we've put in our regression equation, part B is saying to interpret the slope and the y-intercept if appropriate. So slope means the same thing for every line. It's always trying to show, or it always is showing, how much the y variable will change when x changes by 1 unit. And so that's what slope indicates. And slope, y equals mx plus b, it's the number right in front of x. So this is our slope. And so if x changes by 1 unit, in this case that means the weight of the car increases by 1, y will change by this much, which means it goes down by 0.00805, which makes sense. If our weight goes up by 1 unit, our gas mileage probably will go down some. And this is what the regression line says, is the amount the gas mileage will go down for every 1 pound increase in weight. Now, this part about interpreting the y-intercept if appropriate, the y-intercept is on the y-axis. That means x is 0. So it doesn't make sense for our x value to be 0. If so, we would interpret this is y would equal 46.43 when x is 0. So the gas mileage would be 46.43 when x is 0. Now, it doesn't make sense in this situation for the weight of a car to be 0. That's impossible. So it doesn't make sense to interpret an x value of 0 in this context. For part C, they give us information about a specific car, how much it weighs, and what its miles per gallon is. And so enter in the weight for x here into the regression equation. So I'm entering 3,600 here, multiplying it by the slope and add the y-intercept right here. And the regression equation gives me back a prediction for what the average car that weighs 3,600, this is the gas mileage the average car that weighs 3,600 will get. And so part C is asking, for this particular car only gets 15 miles per gallon. Is that above or below this average that we expect based off of the regression line? And since 15 is less than that value, this particular car is below average for cars that weigh 3,600. And part D is saying, would it be reasonable to use this regression equation here for hybrid or electric cars? And the answer is, it wouldn't be, because all of our data is based off of gas-powered cars. So this should only be used for gas-powered cars. You wouldn't want to plug in the weight of a hybrid car here to try to predict what its gas mileage is. Another thing that's not reasonable to do is to plug in x values that are really far outside the range of the data. So if we looked at these x values, like the smallest one appears to be about 2,600 100, and the largest one looks to be around 3,800. So you would plug in any x value in between those ranges, and you would get a reasonable calculation back for the miles per gallon. But if you had a heavy car, like a 10,000-pound car, it would not make sense to use this same regression equation because we don't have any data in that range. Or if you had a car that's below 2,600 pounds, a 1,000-pound car, that doesn't make sense to plug in either because we don't have any data for cars in that range. For number 9, we're looking to see if there's a relationship between the number of cans of soda consumed in a week and then bone mineral density for women. So we'd want to look at our table of data and open it in StatCrunch. And then from there, stat regression, we're looking for a linear relationship here. And our explanatory variable, number of colas per week, we're going to use that to see if we can predict what the bone mineral density will be. So we hit compute, and right away we get our regression equation. And so with that regression equation, let's start by interpreting the slope. Slope is always going to be how much is y changing when x changes, increases by 1. So x is the amount of soda that someone drinks in the week. So for each one more cola consumed in the week, bone mineral density will, and it's going to change by, the y value is going to change by whatever the slope is. And since it's negative, it's decreasing, and then it's decreasing by the amount of the slope. For interpreting the intercept, that is when x equals 0. We always need to ask ourselves, does it make sense for x equals 0? In this scenario, it would be someone drinking 0 cans of cola in a week. That makes sense. That's definitely possible. So if we plugged in a 0 for x, y would equal the y-intercept value here, this constant number. And so that's the interpretation of the y-intercept. If someone drinks 0 cans of cola in a week, this is their predicted bone mineral density. In part D, we want to predict the bone mineral density for someone who consumes 4 colas a week. And so the least squared regression line is what we use to make predictions. So just plug in a 4, because we're looking at 4 colas per week. So 4 is our x value we're plugging in. So plug that in and do the computation, and it gets back what the predicted y value is, the predicted bone mineral density for someone who drinks 4 colas a week. Now, it says researchers found a woman who consumed 4 colas per week and had a bone mineral density of 0.873. Is this woman above or below average? So this is the predicted average for people who drink 4 a week, 0.8746. And so 0.873 is less than that. So this particular woman is a little bit below average out of the women who drink 4 colas a week. For part F, would you recommend using the model that we found, this least squares regression line, to predict the bone mineral density for someone who consumes 2 cans of colas per day? So notice here it's asking per day. So that would be 14 a week. Now we don't have any data for anybody drinking more than 8 a week. So 14 a week is outside the scope of our data. We would not want to use this model for someone drinking more cans of cola than is outside the scope of our data, which our highest we had was someone drinking 8 a week. So the answer for that question would be no, this model's inappropriate for 14 a week. One last thing I want to point out before moving on, in this problem, the correlation coefficient, we had about 0.80, and for a sample of size 15, we just need to be above 0.51 to conclude that there is a linear relationship here between the variables. So we did meet that criteria with our critical values. In number 10, we have data about the number of days someone missed from a class and then their final exam score. So we want to open that data in StatCrunch, and then we're going to find the simple linear regression here. So stat regression simple linear. And so we're trying to use the number of absences to predict our response variable here, the final exam scores. So we hit compute and we get our least squared regression line. We also have a really high correlation coefficient. So we're good to go here, assuming there's a linear correlation. Now we're going to interpret the slope and the y-intercept. Slope is how much is the y variable going to change in value when x increases by 1. So for every additional absence, that's a change in x by 1, a student's score is going to drop because we have a negative slope, and this is how much it drops by, the value of the slope. And then interpreting the y-intercept doesn't make sense in this context for x to be 0. That would be someone with no days absent. That definitely happens. We have perfect attendance. And so that does make sense to plug in a 0 for x. And then our y-intercept here, the expected score for someone with 0 absences, is listed there. Also notice that 0 is within the scope of our data. We had some students in our sample that had 0 days absent. So this is a good model for someone with 0 absences. It makes sense to interpret our y-intercept. So now predict the final exam score for a student who misses 5 class periods. I'm going to plug in a 5 here for x. And so doing that in a calculator or Excel, plug a 5 in where x is. So for 5 days absent, we predict a student's final exam score to be a 74.33. Now it says to compute the residual, so it's asking how far is someone in our actual sample of data who had 5 absences, how far away are they from the prediction? So they had a 74.5. 5 absences, 74.5 in our actual data set. So computing the residual means to take what we had in our actual data set and see how far away it is from the prediction. So just subtraction there. And we come out that it's a 0.17 difference. So is that final exam score above or below the prediction for 5 absences here? And you can tell because it's positive that it's above on the prediction. You can also just look at it. 74.5 is greater than this. It's above that score. The next question is about drawing the scatter plot with the least squared regression line, and you can get to that here in StatCrunch. And just notice where the points fall above and below the line, and you can match it up. The scales are a little different, so you don't get the exact same look, but the way the points fall above and below the line will be the same. And finally, is it reasonable to use our equation here, our least squared regression equation, to predict the final exam score for a student who missed 15 class periods? And remember, we only want to plug in x values that are within our scope of data, which runs from 0 to 9. And so 15 is larger than our highest data value for x, and so we don't want to plug in 15 into that equation to try to predict the y, the final exam score.